Hello everyone, welcome you all. Today we are going to discuss the problem cycle finding from CSES Graph problem set. Let's go through the problem. You are given a directed graph and your task is to find out if it contains a negative cycle. And also you have to give an example of such a cycle. The input contains two integers n and m, the number of nodes and edges. The nodes are numbered 1 to n. After this, the input has m lines describing the edges. Each line has three integers a, b and c. There is an edge from node A to node B whose length is c. In output, if the graph contains a negative cycle, you need to print yes and then the nodes in the cycle in their correct order. And if there are several negative cycles, you can print any of them. If there are no negative cycles, you need to simply print no. The number of nodes are in the range of 2500 and number of edges are in the range of 5000. Nodes are numbered 1 to n. Edge weights are from minus 10 power 9 to 10 power 9. So let's first of all try to understand what the problem is and then we can see how we can actually solve this. So this is, I have just copied the input that is given in the problem and drew it in the form of the graph. So this is how your input looks like. Now, what do you mean by negative cycle? I hope all of you understand what do we mean by cycle. Like if you start from a node and if you can return through to that node by covering two or more edges, then you say that it is a cycle, right? So like over here you can see, you can go over here, then over here and then over here. So this is one of the cycle. You can go over here, here, here and return here. So this is one of the cycle. So this is one cycle you have in this particular input. This is one of the cycle you have. Is this a cycle? Is this a cycle? No. Why? If you start from here, can you return here? If you start from here, can you return here? No, right? By covering this particular edges, can you return over here? No, right? So this is not a cycle. This is a cycle. This is a cycle. This is a cycle. We have two cycles in this particular problem. Okay. Now, what do we mean by negative cycles? What do we mean by negative cycles? Negative cycle means if you traverse in the cycle, the total sum of edge weights of the cycle is lesser than 0. So for example, if you travel in this particular cycle, can you sum the weights of edges? 1 plus 1 plus minus 3. What will be the output? 1 plus 1 plus minus 3. It will be minus 1, right? This means that this is a negative weight cycle. Similarly, we had one more cycle, right? This is also the cycle that we had. Can you sum up the weights for this particular cycle? It will be 1 plus 1 plus 1 plus minus 2, which is equals to 1. So this is not a negative weight cycle. Okay, this is not a negative weight cycle. So in this particular problem, you have to tell whether negative weight cycle exists or not. And if it exists, you also need to print the cycle. So like for this particular example, the negative weight cycle exists. So my output will be yes. And what is the cycle? Let's start from 1. So you start from 1, you go to 2, then you go to 4 and then you return to 1. So this is a cycle you can print. You can also print like this. You start from 4, go to 1, then go to 2, then print, return to 4. Anything you can print. Okay. I hope the problem is clear. Now how we can solve this? Okay. So whenever this thing comes, negative weight cycle, or whenever you get in problems the negative edges, negative weighted edges, whenever you get these things, one algorithm that should come to your mind is Bellman-Ford algorithm. This is something that should come to your mind. We will see whether we can solve this problem via that or not, but this is one of the famous algorithm that helps you to find single source shortest distance single source shortest distance if we have negative edges in the graph. So earlier what we have seen, we have one more algorithm to get the single source shortest distance, right? And that was Dijkstra. But Dijkstra won't work if you have negative edges. So for that we use Bellman-Ford algorithm. Okay. There is one more use case of Bellman-Ford. It helps you to detect negative weight cycles. Helps to detect negative weight cycles. Okay. So I am not going to discuss the complete intuition behind Bellman-Ford algorithm in this particular video. I am going to give you guys a bit of context, but yes, I agree that that won't be enough to understand Bellman-Ford. So the prerequisite now for this video becomes that you know how the Bellman-Ford algorithm works, and then you can return and see the solution for this. Okay. Let me give you a bit of context. If you knew before and forgot a bit, you will be able to recollect the memory over here. Okay. So in Bellman-Ford, what we do is we relax our edges n minus 1 times. So basically, what does relaxation means? Relaxation means that if you have node U and from there is a directed edge to node V, and let's suppose this edge has a weight of W. So relaxation means that if U is reachable, we relax only if U is reachable. So if U is reachable, then we check that is distance of V greater than distance of U plus W. If this is the case, then what we do? We modify distance of V as equals to distance of U plus W, and this is what we say that we have relaxed this particular edge. Okay. This is what relaxation means. So in Bellman-Ford, what we do, we relax our edges, all the edges sequentially n minus 1 times. Relax our edges sequentially is the very important word. So we relax all our edges sequentially, that is in the order n minus 1 times. And then if in nth iteration we are able to relax any of the edge, this implies that graph contains negative weight cycle. So the basic intuition behind Bellman-Ford is, Bellman-Ford says that if you have performed the iteration n minus 1 times, then from the source you have the shortest distance to every node. Now even after that you are able to relax your edges. This means that you can't reach to you don't have any finite shortest distance to a particular node. It is actually a part of negative cycle. Why I am saying this? See, if I say you that, let's suppose this particular graph only that is given in the input, I've calculated shortest distance. Now just tell me one thing, even after calculating shortest distance, if we have a negative weight cycle, then if we try to relax our edges, the shortest distance will keep on decreasing, right? The shortest distance will keep on decreasing. So you won't have any finite value. So Bellman-Ford says that if in nth iteration we are able to relax any of the edge, then graph contains a negative weight cycle. This is what a basic Bellman-Ford algorithm is. Now, how we will use this in this particular question? In this particular question, we aren't told that we need to find the shortest distance from a particular source and the graph contain negative weights. This is not what the problem is, right? The problem is that you have a graph You need to detect whether it contains a negative weight cycle or not. You only need to detect. Okay, cool. So, okay, so how we can do this? See, if you are following a simple Bellman-Ford algorithm, you can still detect. You can still detect whether the graph contains the negative weight cycle or not. If in nth iteration you are, if in basically nth iteration you are relaxing your edge, you can still detect whether the negative weight cycle or not are present or not. But what is the issue over here? What is the issue over here? Let's suppose this is the graph you have. I'm not marking the edges right now. I'm not marking the nodes or giving the weights to the edges. But let's suppose this is the graph you had. Let me mark the nodes for now. Let's suppose this is node 0, 1, 2, and 3. And let's suppose this is not a complete graph. There can be different disconnected components, right? So let's suppose this is the these are nodes 4, 5, 6, 7. Okay. Let's suppose this is the complete graph you have having 7 nodes. Now, what do we do initially in Bellman-Ford algorithm? Again, I am saying just please go through the Bellman-Ford once if you don't have any knowledge of how it actually works. But if you have gone through, then you will understand it over here. What does Bellman-Ford does? We have a source, right? Let's suppose 0 is the source. So we initialize our distance vector with all values as infinite. Okay, all distance of I becomes infinite. And we mark distance of 0 as 0 because this is our source. So just tell me one thing. If I'm marking distance of 0 as 0, and if you just remember, we are relaxing our edge. We were relaxing our edge only from U to V only when U was reachable. Now, how will you understand whether U is reachable or not? U will be reachable if its distance value is not infinite. If its value in the distance vector is not infinite, this implies that node U is reachable. Now just tell me one thing. If you have marked distance of 0 as 0, you have only marked distance of 0 as 0, then you will be able to detect negative weight cycles only in the component that contains this node 0. You will be able to detect negative weight cycle only in the components that contains this node 0. If there is a component that does not contain this weight 0, and if it contains negative weight cycle, you won't be able to detect that. This is what the issue in conventional Bellman-Ford that we have. Okay. We will make a slight change in the algorithm and the things will work. What is the change? While relaxing our edge, we will just neglect this particular condition whether U is reachable or not. If we do this, just agree that we will be able to detect the negative weight cycle. And why? We are not checking whether U is reachable or not, right? Now just tell me one thing. If you have an edge that has a negative weight, if you have an edge, or let's suppose if you have a cycle and the total weight of the cycle is negative, that is, it is a negative weighted cycle. So it does not matter what the initial distance you have assigned to this particular node. In nth iteration, it is definite. In nth iteration, it is definite that the distance will decrease. That is, the relaxation will happen, no matter what is the distance you have assigned. So if from conventional Bellman-Ford, you remove this condition whether U is reachable or not. If you remove this particular condition and just check this particular condition and you are able to relax your edges in the nth iteration, this means that the graph contains the negative weight cycle. So, like many people explain it in many different ways, but this is actually how the things work. If you just see, you are just removing this conventional thing that U is reachable or not. Because you don't want the shortest distance from a particular node. In this particular problem, you only need that whether the graph contains the negative weight cycle or not. So for that reason, if you just simply remove that thing, you will be able to detect negative weight cycle. Cool. So now you are able to detect negative weight cycle, but is that the only problem given in the question? No, right? The question also wants us to print that cycle. So how we will do that? See, we we have seen many problems of how we actually print the cycles, right? By maintaining the parent. And that is the same thing that I am going to do in this particular problem as well, by maintaining the parent. But there is a slight twist. Let me say you why. Let's suppose this is the graph you had. Let's suppose this is the graph you had. Okay. Let me number the nodes 1, 2, 3, 4, 5, 6, 7. And let's suppose this is a negative weight cycle. Okay. Now what I am doing? I am relaxing the edges for n minus 1 iteration and just seeing that whether in nth iterations as well I have relaxed my edges or not, right? And let's suppose I am also maintaining the parent. Let's suppose I completed the nth iteration. I completed the nth iteration and the last edge that I have relaxed is this. This is my last edge that I have relaxed. So what will I do? If I know the last edge I have relaxed, I also know the node where that edge takes me. So that particular edge takes me to 3, right? So what will I do? I know the parent of 3. I know the parent of 3. So I will go from parent of 3, I will go to 2. From 3, I go to 2. From 2, I know the parent of 2. It will be 7. It won't be 1. Because we have performed the nth iteration. And if, and the weight of this 2 should have definitely, this particular edge should have definitely be relaxed. Because this is a negative weight cycle, right? So definitely I will have the parent as 2. So I go to 7, then from 7 I go to its parent 4, and from 4 I go to its parent again 3, and I will simply reverse this because I need to print a cycle. So 3, 4, from 3 to 4, from 4 to 7, 7 to 4, and 4 to 3, and this is the cycle that I will get. Parent, this is the cycle that I will get. Why I am getting parent of 2 as 7 only? Don't get confused, because in the nth iteration I have relaxed all the edges, and this particular edge would not have been relaxed, but this particular edge should have definitely been relaxed because this is a part of negative weight cycle. So parent of 2 will be definitely 7. Okay. This is when I have relaxed this particular edge. It may be that you have relaxed this particular edge in the nth iteration. It may be, right? Because this can also contain the negative weight. So this is not the part of the cycle. This particular node is not a part of the cycle, right? So how will you reach to a node that is part of the cycle? This is not in your control, right? Which particular edge you are relaxing. You were simply following the sequential order of edges that was given to you, and you were performing relaxation on the basis of that. So you don't have the control over the node or the edge you relaxed at the end, right? So let's suppose you came over here. This was the last edge that you relaxed. So you will have that, okay, node 5 is the last node whose distance is getting updated. But this node 5 is not the part of this particular cycle, right? Then how will you actually reach to this particular cycle? So for that, what I will do is, I will run this particular thing. Let's suppose this is the node I am in at the end. I will perform node equals to parent of node n times. And if I do this, I am pretty sure that at the end, whatever node I will get, that will actually be the part of the cycle. And let me explain you why. Let's suppose this was the graph you had. Okay. And in the worst case, what can happen? That there is a self loop cycle, right? This is the worst case that can happen. Let's suppose this was the last edge that you relaxed. This can be the case, right? That this is the last edge that you have relaxed. Okay. So you want to reach over here, right? Because the cycle exists over here, you want to reach over here. So let me see how many times you have to go to your parent. There are 4 nodes, right? From here you have to first of all go over here to its parent. From here you have to go to its parent. From here you have to go to its parent. So just going n minus 1 times only, you are able to reach to a node that is actually the part of negative weighted cycle. Let's suppose this has a negative weight. So you are able to reach to a node that is actually a part of negative weight cycle. So for that reason, I am saying that if you are performing this iteration node equals to parent of node n times, it is pretty sure that you will be able to reach to a node that actually belongs to the negative weight cycle. If you from here, if you go over here, now just don't think that you will go out of the cycle. Just don't get that thing in your mind, because in this cycle, every node is a parent of itself, like of a node. Every node has a parent that actually belongs to the cycle. So don't think that you will go out of the cycle. Even if you are performing more number of iteration, you will be revolving in this particular cycle only. So at the end, you will be present in the node that actually belongs to this particular cycle. So this is how you are going to solve this problem. You're first of all going to go to a node that actually belongs to the cycle, and then you are just simply going to go to its parent and go to its parent, push the nodes to an answer vector, then reverse the answer vector and print your answer. So this is how actually you are going to solve this problem. So the main thing or the main confusion that people actually get in this particular problem is that we are told that, okay, Bellman-Ford is a single source shortest path algorithm with negative weighted graph, in a negative weighted graph. So how so over here, since we want to detect the cycle, then like there, if I assign distance of 0 as 0 and rest all other distances infinite, then will I be able to identify the negative weighted cycle that does not contain the node 0? That is actually not a part of the component that has 0. So this thing should be clear, that what happens in Bellman-Ford, if you understand the underlying algorithm where you are relaxing the edges, so edges relaxation will happen in nth iteration if it contains a negative weighted cycle, right? No matter what is the, definitely you won't get the shortest distance from your source, that is 0, if it is part of a different component, but relaxation will happen. And in this particular case, we only want that whether relaxation is happening or not to detect the negative weighted cycle. So this is what we are doing in this particular problem. Okay. So let's see the code for this so that the things become more clear. So I am taking inputs of number of nodes and edges. Then I have constructed a vector of array LL3. This basically means that you have 3 elements. You have an array that contains 3 elements. So in my vector of this T, I am constructing, because my edges will contain the starting node, the ending node, and the edge weight of the edge. So taking the inputs and pushing back in my edges. Then I construct a parent vector. Initially, I am following basically the one based indexing that was given in the problem. So size is n plus 1, and initially the parent of every node is, let's suppose, minus 1. And distance vector, where again the size will be n plus 1 and initializing it to 0. Now don't get confused. Even if I write something like this, where I am initializing all the values to int max, and then I am initializing distance of 0 as 0, the things won't get changed. You will still get the correct answer. Okay. Just for convenience purpose, like just to look better, I am just initializing all the values to 0. Then initializing my x equals to minus 1, doing n iterations. Okay. So why I am initializing this x, you will understand. So after every iteration, I am just re-initializing my x to minus 1, going over all the edges and performing the relaxation. So u is the first node, v is the node where this particular edge takes me, and this is the weight. Now see, I haven't kept this condition whether distance of u if not equals to int max. I haven't initialized only it with int max, but even if I would have, I won't have kept this particular condition, because I am not checking whether u is reachable or not. I am only seeing for relaxation. Okay. So if distance of v is greater than distance of u plus w, this means I need to relax this particular edge. And the relaxation node, the node that is getting relaxed is v, right? So I am initializing my x to v, or modifying my x to v, modifying the distance and modifying the parent of v as u. Once you're done with this, so see, at the start of the nth iteration, you have reinitialized your x to -1 and you have again performed the relaxation for edges. So if x is equals to -1, this means that in the nth iteration, there was no relaxation and hence your answer will be no. Otherwise, your answer will be x. You need to move x now. Just to ensure that x belongs to the cycle, you simply move x back n times. So you simply run it and you change x to parent of x n times. Now you need to simply print a path. So path vector, current node is x. Now while it is true, in your path you are pushing back current and you're shifting your current to parent of current. If you have reached to a point where current is equals to x, then you simply break because you have reached to the point from where you have started. Now we know that since we have constructed a cycle using the parent, so we have the reverse path right now. So to get the correct path, we simply reverse the path vector, print the path. So printing will give me this. Like if you have started from 2, so it will give me 2, 3, 4, 7. But to complete the cycle, you again need to push this 2 over here, right? So this is what I am doing. I am again printing path of 0 and this closes the cycle. So this is how actually you can solve this problem. Common Bellman-Ford algorithm. The only thing that we have done over here is the only modification that we have done over here is that we have removed this condition whether u is reachable or not, and this solves the problem for me. I hope this is clear to each and every one of you. Thank you.